I want to present you some observations on the green golden rule, which is a concept introduced exactly 30 years ago, which has some interesting aspects to be known, and there are some misunderstandings in its analysis, I think, and it should be known better. This concept was introduced in a research by Beltratti, Cicillinski, and Degli, and concerns a model of growth of an economy with a renewable environmental good, and this aspect of the presence of an environmental good together to the traditional physical good is the key aspect of the ideas of Beltratti, Cicillinski, and Degli. In this model, they discuss essentially two different problems, control problems. One is called the discounted utilitarian problem, and the other is called the long-run utility problem. And discussing this long-run utility problem, which is considered necessary to take into consideration the utility and the interest of future generations, they arrive to the definition of the green golden rule, GGR. So I want to present these different problems, compare their features and their solutions in order to understand what is good in the discussion, the analysis presented and used by several authors, and what is less correct and less usable. To start with, we have that the main paper with the essential aspects of the analysis was published by Beltratti, Cicillinski, and Degli in Economics Letters 1995. The title was exactly The Green Golden Rule. They proposed in this paper an environmental sustainability problem and obtained the definition of the Green Golden Rule, a solution to the problem, giving the highest, in their words, the highest indefinitely sustainable level of instantaneous utility in a framework where environmental goods are valued in their own rights, in the sense that they give utility, and the utility is measured as an essential feature of preference in the optimal control problem which is considered, or the optimal control problems which are considered. The paper in Economics Letters was rather synthetic, and to understand better the context of that paper and of the definition of the GGR is useful to consider two other papers by the same authors, Sustainable Growth and the Green Golden Rule, published as a technical report in 1993, and the Environment and the Long Run, a comparison of different criteria, published in Ricerche Economiche in 1994. Ricerche Economiche was a journal published by the University of Venice, Ca' Foscari. So these are the three papers which are important to understand the analysis, the feature of the analysis of our authors. Why the interest of discussing this research now after 30 years? I already said some about that, but in particular, to me, the interest was arisen by a paper written by Faria and McAdam, published recently in 2018, again in the Economics Letters. And the title was The Green Golden Rule, Habit and Anticipation of Future Consumption. The authors have had the objective of analyzing the robustness of the GGR to alternative consumption preferences. And it seemed interesting for the concreteness of application. These authors, Faria and McAdam, in their paper required the analysis of infinite horizon optimal control problems, but some results were not convincing to me, and I think are not convincing if they are looked at precisely. In fact, the origin of some doubts was to be found in the paper original by Beltratti, Cicillinski, and Degli. A clarification seemed needed to me because of the interest of the GGR idea and because other authors use it, some trusting doubtful results. Further literature that I saw referring to the GGR or the GGR criterion are the following: paper by Ayon Lukama, 2001, Sustainable Growth, Renewable Resources and Pollution. Another paper, more recent, 2013, by Kant and Shahi, Multiple forest stocks and harvesting decisions, the enhanced green golden rule. This presents a generalization of the green golden rule, trusting many statements of Beltratti, Cicillinski, and Degli, in part without checking directly those statements. And the last, most recent paper is by Long, Tidball, and Zakur, titled Optimal Harvesting and Taxation when Accounting for Marine Environmental Quality of the Fishery. The cited papers treat problems which have formal similarities. The first two, in addition to the paper by Faria and McAdam, overlook capital evolution. This is a feature which is negative in our observation, while considering long-run objectives. And this is in agreement with what Beltratti, Cicillinski, and Degli state. The last paper by Long, Tidball, and Zakur refer to the paper by Beltratti, Cicillinski, and Degli for attributing the regulator in their paper the aim of maximizing steady state welfare. But they retain, this paper, they retain information on capital evolution, contrarily with the other papers cited, and in contrast with Beltratti, Cicillinski, and Degli. The second position to me is correct and not the first one, and I wish to convince you of this fact if it is necessary. So let's look at the model. We have two variables with two quantities which describe the state of the system. One is capital, physical capital also called, and the other is environmental capital, the first denoted by K and the second denoted by A. These two quantities are input to the production system, whose output is represented by the function f of Ka, the production function, which provides the production rate associated with the stocks K and A of the two capital variables. The assumptions on this production function are essentially the assumptions of the neoclassical economic growth theory. And so we required, and Beltrati, Cicillinski, and Degli required that it is positive, increasing in each input, and concave. And also that the NADA conditions for the component K of the input hold. Beltrati, Cicillinski, and Degli also assume linear homogeneity of the function f, but in fact they don't use it. It has no meaning in the model. The output from the production process may be consumed, and consumption, denoted by C, depletes also environment, not only the capital as is usual in economic growth model, but also the environment asset. Then, in the view of Beltrati, Cicillinski, and Degli, we have that C is consumption both of capital, physical capital, and of environmental capital. To be more precise, let us consider the motion equations which are discussed and not exactly used in their more general form. For the capital, physical capital accumulation, we have that the motion equation provides the variation of capital as the difference of production capital minus consumption flow and minus obsolescence flow. In fact, Beltrati, Cicillinski, and Hill, for simplicity, choose the parameter delta to be 0, but it is not important in the analysis, apart for some particular considerations on one kind of solution that we will see in the end. Environmental capital evolution is given by a different motion equation, in which we have the negative contribution given by consumption, and we have the first term, the positive term, which is a term of production of environmental asset, and is represented by that function R, which is a growth function. It gives the rate of renewal of environmental capital without giving any other input. We have that the environmental capital is regenerating itself. The assumption for this new function is that it is non-negative, that it is concave, twice continuously differentiable on a domain which is that closed and bounded interval from 0 to AS, with the values at the extreme points 0. Okay, that's all for the motion equation. Then the description of how the true state component of our model evolve in time. Now, as usual in economic growth theory, we have that the flow of consumption is the element which determines utility for the population. And in that case, the authors introduce also the capital stock A as something which contributes to producing utility. So we have this representation of utility associated with consumption flow C and environmental level, capital level A. The utility function U is a twice continuously differentiable function. We assume that it is strictly increasing in each of its arguments and concave with behavior when C tends to 0, which is characterized by the fact that marginal utility of consumption is infinity. Beltrati, Cicillinski, and Degli also suggest some special features of this function, which they do not use, in fact, in the analysis. And in particular, they arrive to suggest that perhaps this utility should be non-increasing in A for particular values of the environmental asset A. But this is not important in analysis. So I remain with what I consider the minimum assumptions for the generality of our problem. Well, with these elements in hand, we can state an optimal control problem, which is the following. This is my formulation of the problem, and later I'll tell the difference with the problem stated by Beltrati and others. I consider an infinite horizon optimal control problem in the sense that optimality is catching up optimality, so that the integral from 0 to infinity of that integral function has always meaning for us, and in particular it has meaning also when the rate of the discount rate rho has value which is equal to 0, and we assume there is no problem of with interpreting a divergent integral possibly. We have the two motion equations which we have already discussed. We have the information on initial state of the economy, and we have some conditions on the admissible behavior of the state functions when t tends to infinity. And we have the condition natural on the non-negativity of consumption flow. We assume also that K naught and A naught are strictly greater than 0, but these, in any case, don't enter our analysis.
Rob, can I ask you a question?
Sorry?
I have a small question.
Yes? Please tell.
In the conditions, you are adding the limit n for K of t and A of t. But K of t and A of t should not be always positive or non-negative?
You may be right. I put those conditions for completeness of the framework, but I didn't want to go into details about the production process. In fact, looking at the second variable, so the second motion equation, we have that it could, in theory, lead to negative values of of A, which are not justified by nothing we have discussed so far, and the situation is similar for the capital K, but I would ask you to consider this aspect secondary.
Okay, no problem. It was really a clarification.
No,
sure.
You are right that we should discuss, we could be interested to discuss these details, but they are not useful in our treatment, and they are not considered in the model used in the literature I've seen.
Okay, thank you.
Well, given this definition, let us see some differences with the paper of Beltrati and others. This can be understood better looking at the first two papers of 1993 and 1994. The problem was stated as the problem of maximizing that objective function that you see, where the parameter rho, the discount rate, is assumed to be strictly positive. And also there is the assumption that the function UCA, the utility function, is bounded above, and it is understood in the lines that they require also that UCA is non-negative, so that with these features we have that the improper integral on the infinite horizon that is used to define the optimization, the objective functional, that functional always converges, and the comparison of solutions is elementary, is the same comparison of real numbers that he used for problems in finite horizon. And this fact that they consider a problem with that convergence of the integral leads they to note that the problem statement is unfair towards future generations because utilities obtained associated with situations C and A far in the future are weighted very small weight because of the feature of the discounting effect. And this is a negative aspect for a model which wants to consider sustainability of, discuss sustainability of the economic system, which means existence and wellness of the economic system when t tends to infinity. In fact, to me, the assumptions of Beltrati and others are unnecessarily restrictive because, in fact, if we use the catching up optimality criterion with rho equal to 0, so we do not discount utilities, this is one way to obtain equal consideration of future generations. And we'll treat this problem together with the problems with rho strictly positive because they have the same a same set of necessary conditions, not apart from transversality conditions. And we call this problem in particular with rho equal to 0 and with the catching up optimality criterion, the total utility problem. Then we will see some consideration about this in comparison with the solution to different optimum control problems. So let's go on discussing the solutions of the problem that we call the discounted or utility problem. So the problem with that objective function and using the optimality criterion on the catching up and using rho both positive or equal to 0. Poltracchi maximum principle conditions are stated as follows. As far as the necessary conditions are concerned, and without considering the special transversality conditions which would be associated with the information on the behavior of the state variables at the when t tends to infinity. We have that, I read something, I don't want to go through all the details, of course. We have that if C star, K star, A star is an optimal solution with the strictly positive value of the consumption function C star, then there exists a continuous and piecewise C1 function mu, two-dimensional, such that for all t in the interval 0 plus infinity, we have first condition which comes from the maximization of the of the Hamiltonian function, which concerns the in particular, the information regarding the marginal utility of consumption. And we have also two other conditions which concern the behavior of the adjoint functions mu1 and mu2, which are those evaluated there, and which involve information both on the utility and marginal utilities of consumption and of environmental asset, and also the information on marginal production of capital and of environmental asset, sorry. Also, in the second of those equations, we have that the information on the marginal renewal rate is concerned. We have also that we have obviously that these first order differential equations are linear. And this is the information that we want to use in order to obtain special information on the solution of the problem. At this point, in order to know more, Beltratti and others look at at constant possibility of constant solutions of the problem. And we will go in the same direction in order to obtain some information comparable with that obtained by Beltratti and others. So we have the following corollary, which is obtained simply by reading the relevant information in the statement of the necessary conditions. We have that if C, K, and A is a constant optimal solution of the discounted utilitarian problem, and if mu1 is the constant adjoint function associated with the state variable K, then First, we have that the motion equations provide us those two relations between between consumption, which is the control of our system, and capital asset physical capital and environmental capital A. These two conditions must hold for each kind of solution, and we are led to distinguish two special kinds of solution depending on the fact that the parameter mu1, the constant value of the first adjoint function, be 0 or different from 0. So we meet a first kind solution where there is no any constraint on the value of mu1, and there are other informations involved which concern both the utility function, so the objective of our problem, and the production function, which is relevant for capital, and rate of renewal function, which concerns the environmental asset. We have also a second kind solution, which is characterized by the fact that mu is equal to 0, and the remaining information is much more simple, as you see, and from the other information disappear the contribution of the marginal production of capital and of environmental asset. Let's look better to these two solutions. Here are the different informations concerning the second kind solution. The first two conditions you see are from the motion equations. Then we have the characteristic of being 0 of the first environmental first adjoint function, and we have the other condition, which is simpler than in the general case of the in which is has a meaningful reading from the economic point of view, which is the following, which is observed by Beltratti and others. The marginal rate of substitution between consumption and environmental asset equals the marginal rate of renewal reduced by the impatience rate. And something of this kind holds also for the first kind solution, and we will see what changes from this solution to the other. We observe that the gradient of production function is irrelevant here. We have that production function is present in the constraints in this, in particular in that first constraint coming from the first motion equation, but nothing else is obtained from this from the production function. So we see there a path for solving the problem and finding a possible constant optimal solution to the problem, considering first the information from the second motion equation, and then the information on that equality that involves marginal utilities of environmental asset and consumption flow, and of marginal rate of renewal of the environmental asset. We have that those two conditions depend on C and A and not on K, and perhaps we could be able to solve them and obtain a pair CA, which is the solution to that system of the two right equations. And we could obtain, in principle, we are able to obtain the pair CA characterized independently of any information on the variable K.
I have a question.
Yes.
So here, what does consumption mean? Like, consumption means a good which is a degrading environment, right? No.
Okay. Please, can you repeat your question?
Yeah. So here, what does consumption mean? C. What does this mean? It's I couldn't understand its intuition.
Oh, this wrong?
C.
C is consumption flow. The consumption flow, which is consumption on the same numerical values, both of capital and of environmental asset. You see that C appears here in the condition which concerns the evolution of capital, and it is present in the same quantity here in the with the meaning of depleting environmental asset.
So consumption is a negative quantity in some way for the environment. It's
when presenting the meaning of the function R, I discussed, and using exactly discussion of the authors that I considered, I only discussed the behavior of R on the domain from 0 to strictly positive value AS, and no meaning was attributed to values of A outside that complex set.
Okay, thanks.
Okay, coming back to our slide, we have that it's possible that the discussion on the system of the two right equations provide a solution, possibly unique or not, CA, independently of any information on K. Then the first equation, this equation could be used with the values found of C and A in order to find the third unknown, which is the value of capital. But nothing guarantees us that a solution of that equation exists. So even if the discussion on the system of the two right equations give a solution, we can observe no second kind solution of our problem. If we look at the first kind solution, then we have a similar framework with the two equation coming from the motion equation. We have something new here concerning the value of the marginal productivity of capital, of physical capital, which must be related to those parameters delta and rho, and must involve also information from the value of capital, of environmental capital A. And we have the other more important from the economic point of view for its interpretation, which compares this expression, difference from the marginal rate of renewal of the environmental asset and the discount factor rho, and this other expression, this ratio, which compares marginal rates of marginal utilities of the two, of the asset A and of the consumption flow C. And in this case, we observed that instead of the equality that we had in the second kind solution, we have a strict inequality because of the fact that we have the F over the A is strictly positive. And we have that mu1, which appear here and here, is strictly positive in this situation. Then we have that the marginal rate of substitution between consumption and environmental asset is greater than, instead of being equal, marginal rate of renewal reduced by the impatience rate. In this case, you see, contrary to the second kind solution, we have that the gradient of production function is relevant, appearing in this equation and in also this condition. We can observe that both kinds of solution are sensitive to information related with capital accumulation, which is present in the set of equations for both solutions, at least through the motion equation condition, which is this condition. This is in contrast with what Beltratti and others say, not exactly with respect to this problem, but with the following, that the stock of capital is not a concern because any stock of capital can be accumulated given a sufficiently long period of time. In fact, we will see soon, discussing of solution of another problem, that the presence of K disappears from conditions, but this is an artificial cancellation of the information from concerning the physical capital. Looking at this, the feature of this problem, Beltratti and the other authors argue that discounted utilitarianism, the feature of this optimal control problem, does not provide the proper attention to the future because future utility are weighted very low. Hence, they want to consider the concern with the long-run values of consumption and environment, and to obtain that, they focus on the non-standard control problem, in which the objective function is stated as you see. They declare that they want to maximize a functional which is defined as the minimum limit of the utility at a particular solution when t tends to infinity. And this is subject to the same conditions as in discounted utilitarian problem. They suggest also other forms of the limit as objective function, proposing them similarly with similar meaning. That's not really important to understand that function, objective function. It's simply important to me to stress the fact that it's not a standard objective functional, and we perhaps do not have necessary conditions for discussing correctly that problem. How do they solve it? They suggest that the long-run utility problem, which has that objective functional, be equivalent to the steady-state utility problem, which is represented below. The problem of maximizing the utility of consumption and environmental asset, subject to those two constraints, which are the conditions obtained from the motion equation of the dynamic problem we had considered, and subject also to other conditions which are relevant to the meaning of the functions which are used, in particular capital F and capital R. And Beltrati and the other authors call green golden rule an optimal solution to this problem. They add to this that what I read you a moment ago, that capital really is not a concern in this situation, because any stock of capital can be accumulated given a sufficiently long period of time. And I do not understand why capital can go by itself, because, of course, the trajectory of capital has consequences on utility. And in any case, if we consider that consideration of Beltrati, Cistrinski, and Degli, we accept that the first condition here, which comes from the motion equation for K, has no any meaning and can be cancelled. So that the problem is the problem maximizing the utility UCA with the constraint that R of A minus C is equal to 0, and also the other the other set constraints for those variables. So Beltrati, Cistrinski, and Degli here impose a strong deviation from the formulation of the problem at the beginning, so that they are not simply suggesting of an equivalence with of the first dynamic problem, the long-run utility problem, with this nonlinear programming problem for some constant decision variables, but also they reduce the information on the feasible set, enlarging it. If we go to consider the Lagrange necessary condition for the nonlinear programming problem, I don't stop here. We obtain the conditions that you see here. So, of course, the constraint of the problem, which are for us using the problem with all the constraints, and we have another orthogonality constraint which involve the one or two Lagrange multipliers, and other two conditions which involve information on the other important functions of the statement of our problem. If we see more deep in detail the meaning of those conditions, we obtain what I show you in a moment, something which is familiar. So we have this corollary. If CKA is an optimal solution of the nonlinear programming problem with C strictly positive, and if it is a regular point so that Lagrange conditions can be used, then we have that the two constraints must hold, and the other conditions may be set in a proper order, and we find that there are two possibilities, two kinds of solution. A first kind solution which is characterized by a strictly positive value of the Lagrange multiplier mu1, and another kind condition which is associated with the zero value of the Lagrange, of that same Lagrange multiplier. And the other conditions are, and these conditions are comparable with those conditions that we have obtained for the steady state solution, or the constant solutions discussed before. In fact, this is exactly the same picture with the addition of knowing the strict positivity of mu1. So you can say that the necessary condition for the steady state utility nonlinear programming problem that we are considering now, possibly equivalent to that long-run utility problem. These conditions coincide with those obtained for an optimal steady-state solution to the discounted utilitarian problem in the special case of undiscounted case where rho is equal to 0. In fact, you see here that the parameter rho is not present, and this is not present here simply because we don't have discounting in the objective function. When we discussed the solution of the constant solution of the discounted utilitarian problem, in that case, we had in the conditions also the value of the parameter rho, which was present. Well, if we cancel that presence of the parameter rho, we find exactly these two descriptions of the two kinds of solution for the nonlinear programming problem. This confirms that optimizing the total utility, which is proper of the undiscounted utilitarian problem, in the sense of the catching up criterion, provides as much attention to the future as the steady state utility NLP problem does. So that approach using the optimal control and with this particular integral to define the objective function is what we should do also if we want to consider properly the features of utilities obtained far in the future. A solution to the necessary conditions, which is either the first kind with that particular condition that marginal production of physical capital is equal to delta and mu1 is strictly positive, or of the second kind with the marginal production of the capital different from delta and with the mu1 equal to 0, which amount to be the regularity conditions in order to being able to use Lagrange multiplier method, well, the solution to those conditions, one or the other, satisfies the second order sufficient conditions to be a strict local minimum maximum point. So we are able to say something more precise about the solution when we have regularity, so, which is when we can discuss the problem with the usual tools of nonlinear programming. In actual context of absence of impatience, which is the context chosen by Beltratti and the other authors, it is still true that both kinds of solutions are sensitive to information related to capital accumulation, which is present at least through the condition which comes from the motion equation, and which we don't see any reason to that can be cancelled. This contradicts the statement in Cicilniski and Dali of the paper, main paper that we are considering, where they say that capital is not important. In fact, capital should be treated as important, in particular because we can see example in which a solution doesn't exist simply because capital with the right features cannot be obtained. This is an aspect which was not understood in the paper by Aaron Lukama, Kanten Shahi, and Faria McAdam, and is something which leads to an erroneous interpretation of results. An observation in the boundary case that delta is equal to 0 when there is no capital depreciation, which is a choice of the model of Beltratti and others, the nonlinear programming steady state utility problem cannot have any solution of the first kind, because it would have that the marginal productivity of capital should be strictly positive, and this contradicts the fact that the necessary condition would require instead that it was 0. On the other hand, that problem may have or not a unique solution of the second kind, characterized more specifically by those conditions. I have an example built with the choice of functions or some choice of functions which are used also by Beltratti, Cicilniski, and Degli. They use the logistic reproduction function, which has that form, which is the unique reproduction function that I have used. I have seen in the literature, and they use the log linear utility function, which is provided in this form with the parameter gamma positive. And I introduced the production function, an additive production function, which is not considered at all by Beltratti and others because they do not consider important the physical capital. And using this function, we find that the environmental capital at optimality is given by that formula, which is strictly positive, as AS is positive. And this is where Beltratti and others stops. But of course, it may be interesting to know also the other components of the solution, which are the capital C star, and we have that we can obtain it in this form. And we have that the capital component must be a solution to the equation that you see there, where A star is already known, C star is already known from the computation we have done before, and we have that the equation may have or not a solution, and in particular we can say that it may have 0, 1, or 2 solutions. The situation is like this one. You see the case here depicted with the possibility that 2 values of k, this k1 star, k2 star, are good for the values of the third component in a problem in which C and A have been found coming from those formulas, and in particular this value C minus F2 of A is situated in the strictly positive part of the C-axis, and not with not too high a value. It's clear that if this point was here, for example, then we won't see any choice of k, so that the function f1 of k minus delta k, which is the left-hand side of the equation, reaches that particular value of C star minus F2 of A. In the case that delta is equal to 0, that equation would be simpler, but in any case, it appears clearly the possibility that the solution exists or not. This was another particular aspect of the statement of Bertatti, Cisinsky, and Hill. They think to find that there exists always a solution. I can't remember if they talk of uniqueness. In any case, it seems that a solution is guaranteed. In fact, this would be so apparently if K is not important in our discussion. My results are published on a paper appeared in Optimal Control Applications and Methods. The title is On an Environmental Sustainability Problems. In fact, that paper contains a mistake. When one discusses or mistakes of others, is of course liable to provide other mistakes himself. Anyway, there is also something good. If you want to look at it, if you want information on the mistake, I'll let you know. I've contributed recently in the discussion which has produced a paper with Fari and McAdam. The title is Monetary Policy, Neutrality and the Environment, published in Journal of Money, Credit and Banking. In fact, I gave a contribution in the beginning, in the introduction of the paper. Of course, I have no any competence in monetary policies, and I don't know what to say of the general results that are presented in that paper. That's all. Thank you for your attention.